To introduce the conduct and output of regression, I'm going to demonstrate how to run an ordinary least squares linear regression. That's regression with a scale dependent variable, and in this video we're going to look at an instance where we have one scale independent variable as well. Subsequent videos will look at cases with categorical independent variables and also at the case of logistic regression for binary categorical dependent variables. So I'm going to show you two procedures to do this. The first one that we looked at in class, and we're going to take the same example, which is the relationship between inequality as measured by the Gini coefficient and union density as measured by the percentage of workers in a trade union. And the first pathway to this is from analyzed regression and then linear. And you'll see here we've got a number of different options before us, and we'll see if we can narrow this down. So first of all, I'll switch to display variable names. And I'm going to transfer my dependent variable into the dependent box up here. Our independent variables go here, and we're just going to look at one. We'll look at the case of union density. Now there are a number of different options I can ask for here as well. Under statistics, I'm going to ask it to give me confidence intervals for the coefficients. I can also, if I want, ask it for collinearity diagnostics, which will show us if any of in the multiple regression context, we would want to look at this because this will tell us if any of our independent variables are problematically correlated. We can also get descriptive statistics for all variables included in the model. But we'll just leave it here at the moment on confidence intervals. In terms of plots, we're going to look at a residual by predicted value plot to assess for homoscedasticity in a moment. So on the x-axis, we're going to put the standardized predicted values. Whenever you see anything with a z here in these windows, this is z-score standardized. So we'll put z, p, or ed on the x, and we'll put the standardized residuals up here in y. And if you want to refer back to the lecture notes, you will find detailed descriptions of what these residuals and predicted values are. We're also going to assess the distribution of the residuals, and we'll ask it for a histogram and a normal probability plot, and then click continue. We can also save, and this allows us to save a number of different things here. If we want to produce our own custom graphics, we can save the residuals in various forms, predicted values. We can also look at influence statistics for undue influence from any cases, and we're going to look at Cook's distance, which is the one we looked at in class. And we click continue and then OK. And we get several pieces of output from this once the procedure runs. And we'll start from the top. So here we have first of all our model summary. It gives us our adjusted R squared, and it gives us a list of the variables included in the model. So you will also need to refer back to your notes for details on how to interpret the adjusted R squared. This varies between 0 and 1, and we can interpret this as kind of a measure of goodness of fit, but also intuitively we could describe this as the proportion of variance in y explained by our, in this case, x or combination of independent variables. We have our ANOVA table that assesses the residuals of different types of models, so the model just using the mean, using our fitted line, and then an assessment of the difference between these. What we're looking for here is our F statistic and to see whether this p-value, the SIG, falls below 0.05. In this case it does, so we have a statistically significant difference in explanatory power from our model relative to the simplest model, which in this case is the mean of y. Our coefficients table appears here, and this gives us the slope for the relationship between union density and the Gini coefficient. So we read this in unit terms. We say for each additional percentage point of union density, there is a reduction in average inequality of 0.111. This is 0.111 Gini units. We also get a confidence interval here for this coefficient, and we get a p-value. We get our and again we're looking to see whether this falls below 0.05. We asked it for a diagram of our residuals, so it's giving us this here. It's graphing our residuals on a histogram, and it's overlaying this normal curve to see if there is any significant deviation from normality. It's quite common in small samples, you'll see this. And also especially with the type of data we're using here, which is World Bank data, predominantly wealthy countries with a couple of transition countries, we would expect to see this. The PP plot, which is the percentile plot, allows us to assess the deviation of the observed residuals from what we would expect under the assumption of normality. And basically what we're looking for here is the distance through which these cluster close to the line. We see here there's quite a number of points of departure across this line. Our scatter plot now is showing us a distribution of the residuals, and again, if you remember back to our lecture slides, which I'll show you in a moment, we can first of all assess this graphically, and what we're looking for is equality of variance at all levels of x. We want to make sure that there's no excessive or drift in the deviation, if you like, from 0 to these points. In this case, we have an example of a heteroscedastic distribution of residuals. The variance of x is not the same, the variance of the residuals, in this case y, is not even or not comparable or identical across all values of x. You see the variance increases as we go further across. These points get much further and further spread apart. So this is an indication that we perhaps might have violated an assumption of the linear regression model, and it's something we might want to take account of in our reporting. Now, the other way to do this, and the way that we will look at later on when we get to looking at categorical independent variables, is we can use the GLM procedure. So this is under Analyze General Linear Model and Univariate. And again, we'll switch to variable names. So in this case, we need to make a few adjustments to this to get both our table of coefficients and to get the model to report the way we want it. In other words, to get the same output as we got here. And there will be some differences in the output. Some of the items are in different places. We have to request certain bits of output that are automatic in the procedure we just saw. So I'm going to transfer my dependent variable over here. And in this case, we want to make sure any of our scale independent variables go in the covariates box down here. So we'll transfer union over. Now, what we're going to look at later is when we have a mixture of categorical variables and scale variables, we want to set up our model properly. I'm going to run through this procedure here just to make sure that we're consistent every time we do this, especially if you're adding more variables to the model, which you will be doing for your assignments. So I click on model, and I'm going to switch this to build terms and transfer all of my different factors over here into the model box and set this to main effects. And then we click continue. We can ask it for a number of different things as well. We can set up some customized plots here if we want. We can also save, and what I'm going to do is here I'm going to save our values for Cook's distance. I'm going to save our standardized residuals, and I'm going to save the predicted values as well. We can graph those later on to check for heteroscedasticity. Click continue, and then one of the most important options, we have to ask it to return a table of parameter estimates. We can also get our descriptive statistics if we want here. I'm just going to leave this by default on parameter estimates for the moment. Once you're happy with all your settings, we click OK. And you'll see here that we get a number of different things or different table pieces in the table of output. So we see here our ANOVA table from the OLS procedure gives us our residuals for the difference between the mean of y and our regression model, which is given over here under the sum of squares tab. We get all this information down here as well, similarly just with a different layout. We also get our table of coefficients, and we see here we get again the slope of the relationship between union density and inequality, which is minus 0.111. We see here that's the same as what we got in this table here. The layout is just a little different. Our R-squared is given here under the ANOVA table, and we see here our adjusted R-squared is 0.136. And again, this is the same as what we would have gotten up here in the model summary table, 0.136. You'll notice that it hasn't automatically given us our plots. What it has done is it saved our variables down here, our predicted values for Gini, our standardized residuals, and our Cook's distance. So what we can do now is we can produce that graph manually by going into scatter plot. I'm going to just produce one scatter plot first for the residuals versus fitted values. So I'm going to go down here and I'm going to put ZRE, which is our residuals, on the y-axis, and I'm going to put PRE, which is our predicted values, on X, and we'll produce that graph. And you'll see here we've got something that looks similar to this one. The only difference here is that the predicted values are not standardized. Here we have them in standard deviation units, and here we have them in their original scores, but it still allows us to assess the shape of the distribution, and we can see we have this heteroscedastic distribution here. For information on how to interpret these, you can refer back to the slides for week 11, and you'll see this excerpt from Andy Field where he talks about different instances where in the residual versus fitted plot we can see the regression assumptions are met. We've got this kind of characteristically random distribution. We have an example of a heteroscedastic distribution, a nonlinear distribution, and one where we have both nonlinearity, this kind of curvilinear drift here, and also heteroscedasticity, this difference in variance across levels of x. So we see here in our case we've got a kind of a classic example of this heteroscedastic residual distribution. Finally, the last thing we want to do is to have a look at our measures of influence. If there are any influential cases that might be biasing that model, cases with extreme values. We go up here to Graphs, Chart Builder. I'm going to produce a histogram of, a box plot of Cook's distance by putting the simple box plot option up here and then taking the Cook's distance and dragging that over to Y. And the box plot is useful because it identifies for us significant outliers with their case numbers next to them. In this case, we don't seem to have any issues because we don't have any Cook's distance that is greater than, that is close to or greater than 1. So this model appears to be okay in terms of undue influence. But again, the issue might not necessarily be in strict diagnostic terms that the Cook's distance is okay. We obviously have a highly selective sample of countries here that we would want to be careful about. So this is how to conduct and interpret ordinary least squares linear regression with one scale independent variable.